All right, time to get started. Welcome back, everybody. I have some old graded papers that people weren't here to get back when I was giving them back. So if you feel like you're missing something, some people didn't get your second test back, let me know. I got it. We do have a homework assignment due tomorrow. I hope you've had a chance to get started on it. Something is weird going on with the website. So it is not visible. I tried to post it and it didn't work. I'm talking to some folks about that. But in any case, I emailed it to everybody, so you should have the assignment in your email. Sorry for the technical difficulties. We're going to have an assignment tomorrow. There will be a quiz on Friday, as usual. And then next week, we will also have a homework on Wednesday and a quiz on Friday. Any questions about any of that? All right, let's get to it then. I want to talk some more about Hamilton circuits. And in particular, I want to talk today about Hamilton circuits sort of in the real world. We haven't really talked about what might be useful about Hamilton circuits in the real world. We did do some like vaguely real world examples involving Euler circuits. Remember, an Euler circuit is one which uses every edge without repeating any edges. A Hamilton circuit uses every vertex without repeating any vertices. And actually, the Hamilton circuits are a little bit more interesting or more useful in the real world, as far as I can tell, in my experience. Euler circuit is when you want to cover all the edges. This is like a Mr. Plow or something. You want to go down all the streets. But actually, there are not many scenarios in life where you want to drive on every street once or use each bridge once. That doesn't happen very often. Hamilton circuit, though, is more applicable in the real world. This is any kind of route planning where you need to visit each place once. There are certain locations you want to get to, and you want to go to each one of them once without repeating any. That actually is much more ordinary scenario that people encounter in ordinary life. Any route planning where you want to visit locations and visit each place once. All right, this is much more a much more common scenario than saying I have a bunch of streets and I want to go across every street once without repeating any of them. I suppose that happens for some scenarios, but this is more common. I have a bunch of places I want to go to, and I want to go to each place once and then come back to where I started. For example, here's a sort of made-up example, but based on a true story. Let's say here is this is me, my house, where I live in the great town of Fairfield, Connecticut, home of Bigelow Tea. I used to live in Shelton, Connecticut, home of the wiffle ball. Now I live in Fairfield. And let's say I want to visit all the people in my family. So I got my parents who live near Boston. That's where I grew up. My parents in let's say in Massachusetts. All right. We also have my wife's parents, which are say down here in this is the in-laws. Can you see them down there? Yes. And that's in New Jersey. And then other family member I got is Aunt Megan. Aunt Megan lives in Pennsylvania. All right. And let's say I want to, of course, starting and finishing at my house, I want to visit all of these people, the other three locations. All right. And I could drive from one to the other any way that I like. I could go, and I'm going to try to indicate that by these sort of lines. Now, these lines are not literally, I would not drive in a straight line, of course, but the lines are meant to represent the fact that I could drive from here to New Jersey, or I could drive from here to Pennsylvania. There should be a line there also. Or I could go straight all the way from New Jersey up to Boston like that, all right? So there's, this looks like a graph with 4 vertices. And what I want to do, what I want to do is make a Hamilton circuit in this graph because I want to visit each of the vertices once and then come back to where I started, all right? So my trip here, my trip should visit each vertex once. Right? And in this scenario, I don't care about the edges, really. It's not my goal to drive each one of those edges. I don't care about that. I care about ending up at each of the vertices one time. So my trip should visit each vertex once without, I'll say no repeated vertices. All right? So what we're looking for my trip is a Hamilton circuit. All right? We don't care about the edges in this case. Because I don't care how many roads I drive on or whatever. I just want to visit each of the vertices. All right? And this is a typical scenario in the real world. This, like I'm trying to say, this is actually more reasonable to have a situation like this than it would be to say I want to cover all the edges without repeating any edges. That's something that most people don't really care about. Here's another sort of more realistic. I don't know. This is perfectly realistic. This is all my family except for Uncle Dave. I left out Uncle Dave. Sorry, Uncle Dave. I just didn't want another thing on the diagram. I don't go to Uncle Dave's house very often. This is not my uncle. This is my wife's brother. My kid's uncle in my household, referred to as Uncle Dave, not my uncle. Oh, here's another scenario. How about the Amazon delivery truck? Let's imagine you're the Amazon delivery truck driver. What you get every morning when you go to work in your truck, they give you like a list of all the places where you have to go to deliver the packages. I actually looked this up, and apparently Amazon delivery truck guys typically do like 100 to 200 deliveries per day. It depends on if you live in a city or in the country or whatever, but let's say Amazon delivery truck has, let's say, 150 deliveries to make. Each day, right? And you could represent that as a graph also. What you have is sort of like the warehouse somewhere where you park the truck at night, right? But then you have just 150 addresses that you have to go to. And you could go to them in any order that you like. Now, obviously, some orders are better than others, right? But basically, this is a graph. This is a giant graph with 150 vertices plus the warehouse, right? And the driver has to figure out what order am I going to go to all these vertices in. And actually, the driver does not figure this out. When the driver gets to work, they get a big list of all the addresses they have to go to, and then also somebody has figured out the route that they're supposed to drive. The driver doesn't figure that out. All right. But anyway, this is a giant graph with 150 vertices plus the warehouse. And somebody, it's not the driver themselves, but someone figures out the best route to drive. And this is really what I want to talk about today. In theory, the driver could deliver these packages in any order that they want, but some of those orderings are going to be very bad. You want to choose an ordering of the vertices which makes the best sense in terms of either how much time it's going to take, or maybe how much distance you have to drive, or how much fuel you have to use, or something like that. Somebody figures out the best route to drive. I'm going to sort of underline and put in quotes this word best, where the word best may mean different things in different scenarios. Maybe Amazon wants them to go as fast as possible, or maybe they want them to do it in the shortest distance to save fuel or something like that. There are different ways that you could consider what counts as best. But Anyway, this is still about finding a Hamilton circuit, which is somehow the best, or the cheapest, or whatever, the quickest Hamilton circuit among this giant graph of 150 vertices. So this kind of problem, it is super important. Of course, it's not only the guy in the truck at Amazon who needs to do this kind of thing. All kinds of, this isn't the sort of thing that I do in my own personal life from day to day, but all kinds of scenarios in the world require this kind of problem solving. All right. Let's talk a little bit more specifically about my simple scenario. This, of course, is a very big graph that I don't want to get into the details of just because it's so much bigger. But my simple little graph had 4 vertices, remember? And I'm going to draw this graph again just in a square rather than in some kind of true geographic arrangement. But this is my simple graph, which had 4 vertices, and they were each of those locations. Maybe I'll just write the states this time. So I'm going to put Connecticut here, Massachusetts up there, Pennsylvania over there, and New Jersey over there. All right. So this was my graph from before. I am just drawing it in a more simple graph here. But the question, again, that you want to ask here is, which Hamilton circuit uses the best route, right? Route or route. And there are many possible Hamilton circuits that you could make in here. In fact, there are edges on this graph between any 2 vertices, right? Every pair of vertices has an edge between it. And what that means is you can go anywhere to anywhere else. So a Hamilton circuit would look like some specific choice of ordering the vertices, right? For example, I could do, we have to start in Connecticut and finish in Connecticut, but I could do Connecticut. I'll just use the first letter if you don't mind. I could do Connecticut to Massachusetts to Pennsylvania to New Jersey to Connecticut, right? That would be going around the outer edge, counterclockwise. That's one way to do it, to hit all 4 vertices. Is there any other way to do it? Yes, actually there's many other ways to do it. And in fact, you could write any ordering that you like. I could say C, P, N, M, C. Whoa, that's an M here. I did that without even looking at the picture. I'm just writing the vertices in some other order, right? And I know because the picture has every edge actually exists in the picture, and so you can actually do any possible reordering or any reordering. All right. When you have edges everywhere in a graph, you can make a Hamilton circuit by just rearranging the order. Now, I said the C, I said we should start and finish at Connecticut, but other than that, I can rearrange the other 3 vertices in any order you want, and you will get a Hamilton circuit. All right. Can we talk about how many Hamilton circuits there would be in this graph, or let's just because I had to scroll it. Let's say that I have this graph here. Maybe I'll call them A, B, C, D here. So starting and ending at A, the Hamilton circuits are all possible reorderings of the other 3. Of the B, C, and D. So can I try to write them all down? It could be A, B, C, D, A, right? That's just kind of alphabetical order. Or it could be A, B, D, C, A, or it could be A, C. I'm trying to write them all down in some sensible way. A, C, D, B, A. Right, first I wrote the 2 which begin with B in the second position. Then I wrote the 2 which begin with C. And now I could write the 2 which have a D there. A, D, B, C, A, or A, D, C, B, A. All right? There's 6 of them. These are all the possible Hamilton circuits in that graph. There are 6 of them. And what I did was I keep the A on the outside, but each one of these is obtained by rearranging those 3 other letters in some other order. All right? So with 4 vertices, there are 6 possible Hamilton circuits. That 6 has to do with the number of ways that I could rearrange 3 things, right? Because in this problem I had 3 things in the middle there. There's actually, we've talked about this quite some time ago, a long time ago in this class when we were talking about voting. We talked about how many different ways are there to rearrange, say, 3 things or 4 things. Anybody remember what we ended up saying? There's actually a formula, the number of rearrangements. We called these permutations a long time ago in the context of I think we talked about this in, when we talked about weighted voting. The number of rearrangements of, let's say, n things. Anybody remember this? All the different ways that you could rearrange. Say 3 things can come in, you get actually 6 possible rearrangements. The number of permutations. This actually was, do you remember?
I was in combinations.
Yeah, the combinations was something else. That was how many ways you can choose some of them. The permutations there was actually a formula for this. It's the number of rearrangements of n things is n factorial. Remember that thing? That means 1 times 2 times 3 all the way up to n. You multiply all the numbers up to n. That's why in this example there were 3 things in here. 3 factorial is 1 times 2 times 3, which is 6, and that's why there were 6 different permutations in that particular example, because there were 3 things which were being rearranged in the middle, and 3 factorial is 6. All right. So the total number of rearrangements of n things is n factorial. What that means, this will tell you sort of how many different Hamilton circuits you can get in one of these graphs. Let me just say, there's actually a name for this type of graph, a graph which has, what I mean by this type of graph is that the graphs that I've been using here are ones which have all possible edges drawn on this graph. Every pair of vertices is actually connected directly by an edge. That's not true of most of the graphs that we look at before now. But anyway, a graph in which each pair of edges, each pair of vertices has an edge between them. This means that graph, it has all the possible edges. There are no edges that are left out of the graph. Every edge which you might want in there is actually in there. A graph in which each pair of vertices has an edge between them is called a complete graph. This is a graph that actually has all the edges that it could possibly have, other than like double edges or looped edges. It actually uses every edge. Every edge is present between any 2 vertices. That's called a complete graph. And they look like, you could have a complete graph using 3 vertices, would just look like this, a triangle, right? Every 2 vertices there has an edge between them. If you had 4 vertices, it looks like this picture that I drew before, like that, right? That's a complete graph with 4 vertices. If you have 5, it would look like this. So you put your 5 vertices, and then every vertex has to be connected up with every other vertex. It would look like that, I believe. That's a complete graph with 5 vertices. Or 6. You can draw these pictures as much as you want. I'll just draw 6. You draw 6 vertices and then connect every vertex has an edge with every other vertex, like so. Like that. I think I drew them all. All right, those are all examples of complete graphs. That's a complete graph. And what I was trying to talk about is how many different Hamilton circuits will exist. Well, in this one, there are 6 different Hamilton circuits. If you decide to start at a particular place, you get 6 different Hamilton circuits. It has to do with the factorial. For 4 vertices, you get 3 factorial. It's always going to be the factorial of 1 number less. So in a complete graph, with, let's say, n vertices, there are n minus 1 factorial different Hamilton circuits. All right. N minus 1 factorial different Hamilton circuits in a complete graph on n vertices. That's because you choose where to start, and they all are going to start and finish at the same point. But otherwise, you can rearrange the other vertices in any order you like. That's why you get the factorial there. And I just wanted to say, this is very, very many. This number, n minus 1 factorial, is a really big number if the n is big. If the n is 4, this number is 6, which is not so big. But when the n is larger, this number, n minus 1 factorial, becomes very, very large. Even in like somewhat reasonable real-world scenarios, this number is going to be very, very big. For example, the Amazon truck, right? Amazon truck with 150 packages. Remember, this makes a giant graph with 150 vertices plus the home base, where the warehouse. How many total routes are there going to be that the truck could go? There will be 150 factorial. 150 factorial total routes that the truck could choose from. And this is a very big number. All right? How much is 150 factorial? It's 1 times 2 times 3 times 4 times 5 all the way up to 150. I actually typed this into a computer. 150 factorial is a number. This is approximately 10 to the power 262. This is a number, factorial. This is a number with 262 digits. It's a super big number, right? That's how many different routes that the truck could take. And so every day, the driver, it's not really the driver who makes the call, but somebody at the great Amazon corporation, somebody has to choose one of those routes out of this many, which is an enormous, unimaginably large number. All right, that's how many Hamilton circuits there are. These many total routes that the truck could choose from, and we want to find the best one. Right? How many, or how can you sift through that unimaginably enormous amount of different choices and pick out the best one that the guy is actually going to drive? I mean, somebody does this every day, right? For the Amazon truck. So this is the kind of scenario that I want to talk about a bit for the next couple of times. And there's actually a name for this, like, computational mathematical question. Has been around for a long time, and it has a name. This is called the traveling salesman problem. And the idea is, how do we find the best, I'll put this in quotes as usual, the best Hamilton circuit in a complete graph. It's called the traveling salesman problem because this is like from back in the day when there were like door-to-door salesmen who'd come to your house and try and sell you like an encyclopedia or something. those guys, what they did was every day they arrive in some town and they have maybe 10 different addresses that they have to go to. And it's up to the traveling salesman himself to decide in what order am I going to go to these 10 different places. And you want to do it in the fastest way, or maybe the way which uses the least amount of distance or something like that. So this is called the traveling salesman problem. How do we find the best Hamilton circuit in a complete graph? Where best means the least distance, or maybe time, or maybe cost, etc. Depending on exactly what you're trying to do, there may be different ways of judging what counts as best. But it could be anything. All right. The way that we're going to typically set up a problem like this, so I want to do some examples where you actually have a scenario and you figure out what is the best route. Typically, this is the scenario here is represented by what we call a complete weighted graph. Complete is what I said before. It just means that it has all the edges in it. There are no missing edges. But weighted means that each edge has what we call a weight assigned to it. So for instance, here's my little graph of me visiting my family members, except for Uncle Dave. So here's Connecticut, and New Jersey. And I looked this up. The distances, I looked up the actual distances from one place to the next from the towns, not from one state to another, but from my town in Connecticut to my parents' town in Massachusetts. I looked it up. It's 156 miles. All right, so I'm going to just put that number on this edge. That means that this edge represents a distance which in reality is 156 miles. All right, even though I'm not trying to draw it in the same shape as the true road, that's the distance. I looked up the other numbers and I will tell you what they are. From New Jersey to Connecticut, the distance is 152 miles. It was actually our goal when we moved here to live equal distance between my parents and my wife's parents. And we did pretty good, I would say. From Connecticut to Pennsylvania is 194. That's that diagonal distance. The other diagonal from Massachusetts to New Jersey is 315. The distance PA to MA up top is 355. And then down the left side, PA to New Jersey is 114. All right? This is what we call a weighted graph. And those numbers are the weights. That number right there is the weights. In this particular problem, they represent distances, but in other problems, they might represent time or cost. It's something that you want to minimize, all right? So we want, in terms of the graph here, we want a Hamilton circuit with minimal weight, right? We want a Hamilton circuit with minimal total weight. If you add those numbers up, that would be the total distance is as short as possible to still visit all the peeps. All right? How do we figure it out? Well, actually, we're going to talk about a few different methods for deciding what is the Hamilton circuit with minimal weight. But for now, we might as well start with the simplest way to do this. The simplest way, or the easiest way, I'm going to say simplest rather than easiest. You'll see why. The simplest way is to simply write down all possible Hamilton circuits. Write down all Hamilton circuits. And find the weights for each one. And then you just choose the smallest one. All right? I say this is the simplest way. You'll see actually this kind of takes some effort, although it's not really hard. You just have to do it, and it'll take you a few minutes to do it. But this is the simplest way to find the best Hamilton circuit would be to just write down all of them and decide which one is the best. All right, so let's see if we can do that. I want to keep my picture here, just so I could still see it down here. All right. I am going to write down all of the different Hamilton circuits that you could do. I'm going to abbreviate the states again. So let's start with C. Maybe I'll do kind of an alphabetical order here. CMNPC. That's one way to do it, right? Connecticut to Massachusetts to New Jersey to Pennsylvania to Connecticut. All right. I want to write down all different possibilities. There should be 6 of them, right? So that one, I'm going to leave a little space there because I'm going to add up the weights for each one. But I could also do CMPNC, right? That's the other one, which goes M first for the after the C, of course. Then I could go CNMPC or CNPMC, or I could put P's next, CPMNC or CPNMC. I believe those are all the different ways that you could reorder this. All right? And now for each of those, I'm going to add together the weights, and then we'll see which one is the best. So the first one, CMMNPPC. You have to look at these as individual edges, and there are 4 of them. C to M is 156, plus M to N, that's going down the diagonal, is 315, plus N to P is 114, plus P to C is 194. I hope you all see how I did that. You take each of those individual trips, C to M, M to N, etc., and you add them all together. This I added up on my paper. I got 779 for the total weight for that particular one. All right? And then we just got to do this for each of the other 5 of them. C, M, P, and C. The C to M is, again, 156, plus M to P is 355, P to N is 114, N to C is 152. Add those together. I did this ahead of time. I got 777. How you like that? Those are almost the same, but I suppose the second one is slightly better. 2 miles less total distance. All right. The next one, CNMPC. C to N is 152. N to M is 315, M to P is 355, P to C is 194. These I added up and I got 1,016. So that route is actually much worse than the other 2. All right, keep going. CNPMC. C to N is 152, N to P is 114. P to M is 355, M to C is 156. I hope that you agree this is not really hard, it's just you got to do it. When I add these together, it's 777. Actually, this exactly matches the earlier one up there. That's not a coincidence. Does anybody see why I got 777 for both of those? This is not an obscure coincidence. There's a reason you get the same answer. What do you say?
All you did was just rearrange M and N.
Yeah, that's true.
That's all you did, just switch them.
N and M switched. But doesn't that change all the little numbers? There's actually another way I would look at it. There's some sense in which, like, this one and this one are kind of the same. Anybody, you agree?
I mean, they're both going like from P to N and then from P to M. It's just backwards.
Yes, one of them is just the reverse of the other one, right? If you read this one backwards, you get that one. So they really are the same route, just gone the other way around, all right? So that's why the answers are the same. And in fact, you know, there are 6 here, but actually you don't have to do all 6 because some of them are reversals of the previous ones. Like this one here, CPMNC, that's actually the reverse of one of these, isn't it? It's the reverse of this one. So those, like these 2 are the same. They are reversed. And for the same reason, this one and this one are going to be the same as one another. So this I can say right away, this is 1016. And the last one is the reverse of the first one. And so this one is going to be 779. So in a problem like this, yeah, there are 6 that you have to check, but really you only have to check 3 of them because the other 3 will be reversals of the first 3 that you did. All right? Anyway, what's my conclusion here? So in this case, the best route is CNPMC. That's the 7771. Or equivalently, just the other way around, CMPNC. All right? This route, starting at my house, go to New Jersey, then Pennsylvania, then Massachusetts, and back to New Jersey. Or the other way around. Those are the best routes. And that other one is only slightly worse, right? This 779. In reality, I would say those are essentially equal, but technically this one, 777, is slightly better. All right? This is how we find the best route. There's a name for this procedure that we just did. This is called, I shouldn't have drawn that line. What we just did is, this is called the brute force algorithm. It's called brute force because we didn't actually use any real insight here. You just write down all the possibilities and check them all. So you write down all possibilities and check them. That's called the brute force algorithm. There's no real idea here, or there's no insightful strategy. You just writing everything down and checking everything. This is the simplest way to do it in terms of conceptually simple, although it's kind of annoying to actually do it. But I got one example for you to try. We're not going to do this over and over again just because I said it is kind of annoying to actually do it. But just to make sure everybody is with it, I would like you to try this one. This is totally abstract. Let's say I have 4 vertices, A, B, C, D, and the weights go like this. 1 here, 3 here, 2 here, a 4 here, a 2 here, and a 5 here. All right, and your job is to find the lowest weight Hamilton circuit starting and ending. Let's just say we're going to start and end at A. All right? See what you think. This may take a few moments, but it's not really hard. You just have to work it out. I'll give you a moment and then I'll walk around. Adding together 4 numbers every time. get all of the different routes. There should be 6 of them. All right, can we talk about these? I know not everybody's done, but I had one more thing I wanted to get to today. You should have 6 total of them. You don't have to write them in the same order that I do, although I'm always going to write them in this order to make sure that I get them all. But basically, you have 2 which have a B in this position, you have 2 which have a C in this position, and 2 which have a D in this position. And then we're going to add together the numbers. So I go A to B is 3, B to C is 2, C to D is 2, and D to A is 1. And this adds up to 8. Anybody agree with me? I got 8. I hope that you did too for that particular one. A, B, D, C, A. This would be A to B is 3. B to D is 4. D to C is 2. And C to A is 5. And I add that up and I got 14 for that one. Anybody agree or disagree? Yes. By the way, I wouldn't expect you to add together numbers like in this example on a quiz or something. Those are too annoying to do. I'm sure you could, but I would probably mess it up if I tried to. Smaller numbers like this are more manageable. A to C is 5. C to B is 2. B to D is 4. D to A is 1. So this adds up to 12, right? And I think the other 3 are just repeats of these ones. This one, A, C, D, B, A, is the same as the second one, read backwards. So that's going to be a 14. A, D, B, C, A is the same as the third one backwards. That's a 12. And this one is the same as the first one, which is an 8. And so the best one is the 8 here or here, right? So the best route is A, B, C, D, A, or equivalently, backwards, A, D, C, B, A. All right, those are the same route, really, just driven in 2 different directions. Any thoughts about that? I hope you got those same numbers, possibly in a different order. That's fine. I want to talk about the real world, doing this in the real world, say for the Amazon truck. All right, remember the Amazon truck with 150 packages? The Amazon truck has about 150 packages. Now, if the Amazons wanted to use the brute force method to find the best route, of course, a person wouldn't do this by hand. You would use a computer to do this. But how many different routes would they have to check? The example we just did, we checked 6. Or really, if you want to be tricky, we only checked half of them, so it would be 3. How many routes do we have to check in this case? There are, remember, like I said, about 10 to the, what did I say? Some absurd number. 10 to the 262 different routes. This is a ridiculous number. It's a number with 262 digits, that many different routes that you need to check through to find the best one. Now, obviously, a person could not do this on paper, but even a computer will have a very hard time doing this. If we use a computer, running, computers, this is exactly the kind of thing that computers are good at, like doing the same thing over and over again, adding up a bunch of numbers over and over again. But if your computer is, say, running at 4 gigahertz, I don't know if you're into the gigahertz, this is like the speed of a computer processor is generally measured in hertz or megahertz or gigahertz. 4 gigahertz, I believe, is sort of a very high-end desktop or laptop could run at 4 gigahertz. And that means 4 gigahertz means 4 billion, that's what the 4 billion operations per second. Like if you're mining bitcoins or something, they can do something like 2 gigahertz, I think. And those are like ultra high performance computing instruments. Anyway, let's say, so this would be like a very good computer running at 4 gigahertz. That's 4 billion operations per second. How long would it take you to check through all of these? If you're doing 4 billion per second, actually it's still very long. So checking the routes, checking all routes would take, this is not so tricky to figure out. It would be that big number, 150 factorial divided by 4 billion seconds. That many seconds, right? 150 factorial divided by 4 billion. Because it's this many calculations you have to do, and you're doing 4 billion per second. So it's that many. But what is that number? If you plug this into your calculator can't handle this, but I used a big computer to do this. This is about 10 to the power 245 years if you do this division. That means this is a number with 245 digits. That many years is how long it would take for the computer to check all of the routes and choose the best one. And you have to do this every day for every truck, all right? It takes that many years. Just for comparison, 10 to the power 10 years is the age of the universe since the Big Bang, is about that much. So this number is far, far greater than the amount of time that Amazon actually has to do the computation. 10 to the 10 years is the age of the universe. All right, 10 to the 245 years is an absurd duration of time. So the moral of the story here is the brute force method or the brute force algorithm cannot be used to solve real world problems. You can do it for like 4 or 5 different vertices, but in a real world scenario, which has, say, 100 vertices, there's no way you can use the brute force algorithm. The brute force algorithm cannot be used to solve real problems. You can't even do it realistically with like more than 10 vertices. That's about where a real computer will become useless. All right. The brute force algorithm cannot be used to solve real problems. We're going to talk about some other ways. There are other procedures that you can use other than the brute force, and that's where we're headed next. And I think that'll do for now.